Here is the quotient ring construction from scratch. The setup: let R be a ring, let I be an ideal. Ideal always means two-sided ideal these days. Okay. The basic definition for A, B in R, we say A is congruent to B mod R, mod I, A is congruent to B mod I if the difference A minus B is in I. This is equivalence relation. Equivalence relation on R. So an equivalence relation defines a partition of R into subsets, and the subsets are called equivalence classes. Equivalence class of an element A is also called the congruence class. Congruence class of A is the set of all the elements in the ring that are related to A via this relation. This set is also called the coset of A. Congruence class of A, coset of A. The equivalence class with respect to this equivalence relation, they all mean the same thing. This set happens to be all elements of the form A plus X, where X varies over the ideal I. And a good notation for this set is A plus I for that reason. So we denote it by A plus I, meaning the set of all elements of the form A plus X, X varies over I. Okay. These are the cosets, sets that look like this. Explicitly, these are the sets. R mod I is the set of all these cosets, the set of all these congruence classes, the set of congruence classes. Mod I. Last time we defined two binary operations on this set R mod I. One is called plus. The input is an ordered pair of elements from R mod I, and the output is an element of R mod I. And the other one is called dot. Again, the input is an ordered pair of elements from R mod I. The output is an element of R mod I. We define two of these operations as follows. Given given two cosets A and C in R mod I, choose a little a in capital A and a little c in capital C, and define A plus C to be the coset of little a plus little c, and A times C to be the coset of little a times little c. And we verified, a priori it's not clear that this is a well-defined thing, but it is. We verified that these define two binary operations on the set R mod I. I want you to note that, observe, and this is a crucial observation, that the binary operations on R mod I satisfy the following. The operations plus and dot defined on R mod I satisfy the following. For all A and C, little a and little c, in the ring R, if you want to add the coset of A and the coset of C, then the sum is nothing but the coset of A plus C. And the product of these guys, the product of the coset of A and the coset of C, is the coset of A times C. These two things hold for all A and C in the ring R. So once you know that these operations are there, you can actually work with them just by these equations. The thing is that once I give you a coset, it's not necessary that I give it to you by giving an element little a. So one has to do some work to make sure that there is a well-defined operation satisfying this, and that's why we had to go through all this business on the left-hand side. Yeah, but once you have done this verification that we did towards the end of the last video, you can calculate with them simply by knowing these two equations. Okay? Why though? So can I verify this thing here? You give me two elements of R mod I, so two cosets. Here they are, A plus I and C plus I. How am I supposed to add them? The definition is on the left-hand side. I'm underlining it right now. This is how we add them. Given two cosets, I'm supposed to choose an element from the first coset and an element from the second coset. So choose an element from A plus I. A is an element from A plus I. Choose an element from C plus I. Well, little c is an element from C plus I. So if when I add these two cosets, what am I supposed to do? I'm supposed to pick a representative, and then add them. And then take the coset of that. And that's the sum. That's exactly what we are saying up here. And same for the product. So let's write this down. This is true by definition of plus, since A is in A plus I and little c is in C plus I. Okay, that's all. And now I think I can state the theorem. That gives you this quotient ring with the binary operations defined above. R mod I becomes a ring. And there is a surjective ring homomorphism pi from R to R mod I defined by pi of an element in the ring is the coset of that element for all A in R. Okay. So here's a little bit of the sketch of proof. Well, let's check maybe the associativity of the product in R mod I. So you give me three elements of R mod I. They're cosets, so they look like this: A plus I, B plus I, C plus I. Right? So take A, B, C in R. Three typical elements of R mod I look like this: A plus I, B plus I, C plus I. I need to check that the product in this order is the same as the product in the other order. That's associativity. But up here, you know how to take the product. The product of A plus I and B plus I is just AB plus I. And this AB is the product in the ring R times C plus I. So that's same as AB times C plus I. And similarly, if you do the other one, you're going to get A times BC plus I. But because R is a ring and these are things in R, these two things are equal, so these are equal. So you have associativity, and you can check all the axioms this way. And then finally, what about this? Similarly verify. Verify the other ring axioms. And finally, we have this map from R to R mod I, taking an element of the ring to its coset. And I want to show that this is a ring homomorphism. It's surjective, of course, because every element of the ring R mod I looks like A plus I for some A. So it's equal to pi of A for that A. So it's onto. So pi is onto, that's clear. You have to check that it's a ring homomorphism, meaning pi of A plus pi of B is pi of A plus B, and same for the product. What is pi of A? It's A plus I. So it's a for AB in R, pi of A is just A plus I, pi of B is just B plus I, and pi of A plus B is just A plus B plus I. It's the coset of A, coset of B, coset of A plus B. But we know up here that those things are the same. I'll underline it again in case you missed it. Right here. Coset of A plus coset of C is just coset of A plus C. So coset of A plus coset of B is just coset of A plus B. But that exactly says pi of A plus pi of B is pi of A plus B. And similarly for the product. You could just change the sums by product. Coset of A times coset of B is coset of A times B, which says that pi of A times pi of B is pi of A times B. So pi is a surjective ring homomorphism.